In order to set in motion a merry-go-round, you have to apply some force in the tangential direction. As you know, this force creates a torque that increases the angular speed of the merry-go-round. The harder and longer you push, the greater the increase in angular velocity. In the same way as the force changes the state of linear motion of an object, that is, its linear momentum, the torque changes its state of rotation. So, is there an analog to linear momentum for rotation? The answer is yes. We call it angular momentum. Let's begin by considering a point mass. The angular momentum of a point mass is defined as the vector product of the radius and the linear momentum. Thus, its magnitude will be the product of the magnitudes of the linear momentum and the radius with the sign of the angle between them, and its direction will be perpendicular to the plane containing the other two vectors. It will be pointing upward if the object is moving counterclockwise, and downward if it is moving clockwise. If we express the linear momentum in terms of the mass and the linear velocity, and then the linear velocity in terms of the distance and angular velocity, using the rules of the vector product, we can rewrite the equation for the angular momentum in this way. Now, the product of the mass and the radius squared is the moment of inertia of the point particle. So, we can express the angular momentum in terms of the angular velocity and the rotational inertia of the object. This relation can be generalized for all situations involving rotational motion. Let's now see what happens when the angular momentum changes over time. If we derive the angular momentum with respect to time, we obtain this expression. However, note that the velocity and the linear momentum have the same direction, and hence the first term is zero. The second term is namely the torque applied on the object. Therefore, we conclude that the torque is the change in angular momentum over time. This relation is analogous to that of the force and the linear momentum. This means that if no torque is applied, the angular momentum must be conserved. Note that this is equivalent to Newton's first law. If there is no net force, then the object does not change its state of motion, and linear momentum is conserved. If there is conservation of angular momentum in a system, then the initial and final values of the angular momentum must be equal. Since the angular momentum is the product of the moment of inertia and the angular velocity, this implies that this product stays constant. Remember that the moment of inertia depends on the system's mass and how this mass is distributed, the distance in the case of a point particle, or the shape in the case of an extended body. Therefore, if we change the mass of the system, the radius in the case of a point mass, or the shape in the case of an extended body, we are changing the moment of inertia, and the angular velocity of the system will also change because the angular momentum has to stay the same. In the case of a point particle, this implies that the object will move faster when the radius is smallest. This is what happens, for example, with a planet orbiting the Sun. For the same reason, a skater will rotate faster when his arms and legs are closer to his rotation axis.